Well, greetings everybody. So what you see here is a problem from our assignment on my math lab, and it's a problem that has a lot of detail, and even if I made a very short video about how to solve it, leaving a lot of the explanation out, uh, I guess you would get the kind of the big picture of what to do, but there's so many details for this kind of thing that I hope this video is a compromise between being very quick and to the point, but also providing some of the detail that you could look into further if you needed to. Okay, all right, so here goes. I have a indefinite integral here, and it says to use trig substitution, but from there I have to decide what the substitution should be and how it breaks down and what the ultimate answer is. Okay, so let's do this. I'm looking at it this way. There's my problem as given at the top, and one thing I noticed about it is that it's said to use trig substitution, and often that involves, let's see, there's my suggested formulas from test 1, which you find under modules on Canvas. And there are these guidelines that if I have a difference of squares like so, or a sum of squares like so, then I can apply these trig substitutions like this. It makes it seem like it might be convenient if whatever number you see here, a is going to be a constant in each of these cases, if it is a perfect square. It doesn't have to be, but it seems like it would fit real nicely into this if that was true. So one thing I investigate is, well, it's 361. Is that like something squared? Because it would seem to fit into that pretty nicely if it was. So in fact it is. Root 361 is 19. So what this is x squared minus 19 squared. Now, if I go back and look at my guideline for substitutions, I guess it's like this one, x squared minus 19 squared. In the a there, that constant's 19. So the guideline is, okay, if you've got that, if the integral contains in it somewhere x squared minus 19 squared, which it does in our case, we substitute x as 19 secant theta. Okay, so I made my decision to do that. Okay. Now I'm going to use that substitution. I'm committed to that at this point. X is 19 secant theta, but I have to substitute dx into the integral also. Okay, so I substitute x and dx. All right, I've got in this integral x and dx. Those are two different things. Every time we substitute a variable, we substitute the variable and the differential. All right, so if that's the case, if I'm going to substitute x as 19 secant theta, then dx will be 19 times whatever the derivative of secant theta is, which is secant theta tangent theta. Okay, so into this integral here, I make these substitutions. And if I do that, if I substitute that x right there as 19 secant theta, what's that going to look like? 19 squared secant squared theta, so 361 secant squared theta. And then for the dx, I'm going to put 19 secant tangent d theta. And if I do that, that integral we started with becomes like this. Okay? A lot of simplifying happens in these integrals with trig substitution at this point. In this case, I'll see, well, I could factor out 361 from these terms. And then I get 361 times the quantity secant squared minus 1. But secant squared minus 1, there's an identity for that. It's tangent squared. From here, I actually can apply this root. I can't apply this root from the beginning. There's no rule from algebra that says we can apply a root over subtraction. Okay? Square roots and exponents don't distribute over subtraction. So we're like stuck with that integral with the root the way it is. And that's what makes this one difficult. That's what makes this substitution necessary. But now that I've factored it into multiplication, the root does distribute. Root 361 is 19. Root of tangent squared, tangent. Okay? And that simplifies this a lot. Now, I guess you could say the magic of the trig substitutions is that they allow for these identities to show up. The entire point of this substitution was for this identity to show up there and become something that we can simplify pretty easily. Okay? That's what you would expect to happen when you do this. All right, so I've got this. I've reduced it to this. It reduces further. The tangents cancel. The 19s cancel. And what I get is the antiderivative, the indefinite integral of secant theta d theta. So this substitution, as we would expect if we do it correctly, simplifies this integral quite a bit. Okay, so I end up with that. All right. Now, that still doesn't tell us exactly what to do next. So we get an integral that's much simpler. I have something that's much simpler than what I started with. But how do I solve that? How do I solve the antiderivative of secant theta d theta? It might be you have to use some technique. Maybe you have to use u substitution to do this. Maybe this is some kind of basic formula that we'll just take for granted and we'll apply. In this case, that's true. So if I look at my formula sheet, so this is what we're going to go on right here for the first test. If it's on here, we'll use it. We'll take it for granted. If it's not, we'll work out to some point where maybe the formula sheet can help us. But there it is right there. The antiderivative of secant u du is natural log absolute value secant u plus tangent u plus c. Okay, so we'll take that for granted. It's here. I gave it to you to use. We'll use it. All right. In this video, I'm not going to prove why that works or how you get that answer. We'll just take it for granted for now. So here's your answer. The antiderivative of secant theta d theta, natural log secant theta plus tangent theta plus c. Okay, now at this point, it would make the most sense that if I'm given some problem and the variable is x, that even if I convert to another variable for the purposes of working it, that I would give my answer in terms of that original variable, x. So how do I convert my answer? Because I do have an answer here. This is an answer. It's the antiderivative of the integral that I started with. Okay. I should convert it. All right. I should put it back in terms of x. So how do I do that? The key would be the substitution. The substitution is what changes from one variable to the other, so you can change back. So the trick to converting is just to see what does x equals 19 secant theta do for us. Okay, so all right, let's do this. I'm going to study all the consequences of x being 19 secant theta and see if I can get everything I need to convert this, which is in theta, back in terms of x, the original variable. So my train of thought goes like this. Okay, so x is 19 secant theta. A consequence of that, if you divide both sides by 19, is that secant theta is x over 19. But then if you want to visualize that angle and think about, say, right triangle trigonometry, where we have an angle, adjacent side, opposite side hypotenuse, then you would find secant as hypotenuse over adjacent. That's what it means. And so I guess if you want to visualize that angle, it would have to look like this. The adjacent side is 19 and hypotenuse is x. What about this side over here? Yeah, that's not involved in what I have so far, but this is a right triangle. We're doing right triangle trigonometry. Right triangles follow the Pythagorean theorem. This side squared plus this side squared is that one squared, so I could solve for this one. That's what I'm saying. And now, looking at that, I could find what secant theta is in terms of x and convert this back to x, the original variable. I could also find tangent theta. You know, everything that's here in the answer I have at this point, I can look at this triangle and I can put it in terms of x. And then that was the objective. Okay? So sure, I look at that secant. Well, secant was given to us from the beginning, all right, but tangent is opposite over adjacent, so it's root x squared minus 361 over 19. Okay, so with that being known, I take the answer I have at this point, I use these, I substitute them in, and I've got an answer, which seems like a final answer, now in terms of x, which is the variable we started with. Okay, so it does look like we're done here. Okay, I evaluate the integral, I put it back in terms of the variable I started with. It seems like we're done. But look at this, and it doesn't seem like the answer that's given here at all. Okay, it has some similarity, I guess, but it's not the same. So let's do this. There's more. How do we get that answer? How do we go from this to what I just showed you up there? It will come down to the nature of logarithms and some of the rules that apply to just them, and the nature of this constant of integration. Anytime that we find a general antiderivative, there's going to be this plus c. Okay, why is the plus c there? Well, because what we're saying is if you took the derivative of this, you would get what you started with. Okay, you get all the way back here. That might be complicated. It might be hard to actually show that the derivative of this is equal to the thing you started with. But if it's correct, that is doable. Okay, but if you took that plus any constant, because the derivative of any constant is 0, we add this plus c as just a placeholder to say, well, there could be a constant there. Even if we don't have the information to figure out what it is, it could be there. We have to account for it. So look at this. The way I can show how the answer I got can be reduced to the one in my math lab is with this rule for logarithms absorbed into that constant. So for logarithms, if I have the logarithm of any base of one thing divided by another, I can split that up into an external subtraction. So this thing that I have, given that these fractions can be added and they have a common denominator already, is equal to this. And so I see that I have the logarithm of one quantity, x plus root x squared minus 361, over another, 19. But then I just told you that if that's the case, I can split this up into subtraction externally. So, all right, this is going to be natural log of absolute x plus root x squared minus 361 minus natural log absolute 19, but 19 is already positive, so I dropped the absolute. But then, what did I say that c was? C is some unspecified constant. It's just there to account for the fact that there's a constant that could be there, all right? But, you know, I don't know what it is, and I don't have the information to figure it out. So if I take this out, natural log of 19, it is also a constant. It could be absorbed into this without any problem. And if that seems strange, then you just have to tell me, why would it matter if I'm already saying c is some constant that I don't know? Then I don't know this constant, natural log 19 plus c, any more than I know, or any less than I know plus c. So you can absorb it together and just say, well, all right, well, there's still that plus c at the end. Okay? It would do no harm. That could never go wrong if you do that. And so I get this. So finally, I've got my answer. I had to use this trick to simplify it with logarithms and the constant, but I did it, and that's the answer that is given in the original problem. Okay? All right, so that's how you solve it. There is some fine print that I feel like I should talk about. Why does it say that x has to be more than 19? It didn't just give us the problem. It gave us this other condition that, well, the x can't be 18 or it can't be 17. It's got to be more than 19. So what's the deal with that? I should mention real quick. So if x is more than 19, it works with our substitution that x is 19 secant theta. So secant theta is x over 19. As a consequence, if you violate this, like if you said, well, I'm going to let x be 18. I'm not going to have my x be restricted to be more than 19. What if I put 18 in? Then this would say secant theta is 18 over 19. 18 over 19 is less than 1. And secant of an angle being less than 1 is impossible. It just can't happen. Okay? One way to look at that is the graph of secant theta has a range from 1 to infinity. And if I were to draw more of this graph, you would see this U-shape inverted over here, -1 down to negative infinity. So it doesn't cover anything between -1 and 1. And so secant theta being 18 over 19 is impossible. So this will guard against that. Okay. Another thing is, in another video, it has come up that actually the square root of some unknown number squared is the absolute value of that number. That's true. So the square root of tangent squared of theta should be absolute value of tangent theta. In general, that is a true statement. But why is the absolute value there? Well, because this statement without the absolute value wouldn't work if this unknown in here happened to be negative. The absolute value corrects for the negative and makes it work. So why did I leave off the absolute value in this problem? And on this step right here, let's see, where was it? Yeah, I said the square root of tangent squared, I just said it's going to be tangent. So why did I ignore this general rule about the square root of some unknown number squared? Well, it happens to be that we do know here that tangent theta is greater than 0. X being more than 19, okay? Put your secant theta up here, okay? Putting you in quadrant 1 essentially. That's what happened. That's the short answer. I could go into way more detail about both of these, but this restriction, make sure that we have an answer for secant theta, since that's the substitution we're using, and that we don't run into a problem with the square root of tangent squared. Okay? All right, so that's, believe it or not, that's a short answer. I could provide more detail if needed. Now, last thing I want to say is trig substitution really necessary. It's a lot of work. And I guess, you know, you could use something like Wolfram and find the answer that way, and I don't really have a problem with that. But given that we're in Calculus 2 class, and at least at this point, it's still an objective to work out trig substitution on paper with your own mind, making the decisions and knowing what to do, that, yeah, I would say it's still necessary. Here's a problem I took from a physics book about how to calculate the electric field at a certain point in space if we have like a charge accumulation here on the x-axis. Okay, and here they're using various laws of physics to set things up, and it turns out to be a calculus integral, which is worked at least one way to do it, by trig substitution. Okay, so here's like one example of something real, like a real physical phenomenon with electric fields that involves calculus and specifically trig substitution. Okay, so yeah, is it necessary? I don't know. I'll leave it up to you to decide if it's necessary, but here's an example where we could use it to break down the integral and solve it. Okay, all right, so that's what I have to say about this one. Now, as I said when I started the video, I left a lot out, believe it or not. I can go into way more detail for any of the steps. I'll just need you to decide if that's necessary, meaning if you followed the video, great. If you work a similar problem, great. If you feel like you're getting stuck simplifying, working with algebra, logarithms, trigonometry, all the minor details that you've learned in classes leading up to this point, if that's you, if that's what you're getting stuck with, be sure to let me know so I can help you out with that.